All right, welcome back to ME 104. This is just a quick video to go through the Project 1 description. Um, I, I love the projects in this class. They're super fun. And this is our first one, and I'm really excited about it. All new projects this year. And this is due in 2 weeks on the evening of Friday, the 22nd of January. So the basic idea here is that you're going to design a single component individually. You're going to test it at your house with some of the materials that we listed, upload the test data and video the test, some photos, and then a short report describing the design and why you designed the component this way. And this is a design for minimum mass while meeting constraints on loading and material and manufacturing. So you're really trying to design for mass efficiency here. And we use all the skills we talked about: conceptualization, sketching, simple models, back of the envelope analysis, some CAD and FEA, and you'll use these in an iterative process to design your component. This is a relatively simple project scenario, so each might go pretty fast, but that's good because it'll allow you lots of time for iteration and to focus on the process that you're using itself. And your grades are going to come from objective measures of your component's performance and from your report. So that's the very high level overview. The goals here are to start out with something tractable so you can get a feel for how these projects are going to go, give you a chance to assemble your 3D printer and get it working really well. And this will be the first chance to apply inverse analysis for mass efficiency in component design, and we'll learn more about what that means over the next week or two. All right, so here's the scenario. You are going to design a component to go here between two ropes. So you're going to lift this rope, maybe with your hand or maybe hang it from something, and down here you're going to have a heavy item like a bucket filled with a heavy material, or maybe a free weight or something like that. And that's going to cause a load. And so you'll lift the bucket off the ground, hold it there for 10 seconds. Your component will be in this chain and can't break. So 200 newtons for 10 seconds one time without breaking. That's the thing, with as little material as you can. Now you're going to manufacture your own components using your 3D printer, printing PLA material like the stuff that we send you with the kit. And if you haven't got your 3D printer yet, you haven't got started with it, go to the P3D site and use the Getting Started document. That's the place to start. Here is a photograph of an example setup. Before we do these projects, before we assign these projects to you, I get to do them myself. So I actually did this project this afternoon, and this is the testing rig that I used just to give you a sense of what one might look like. All right, so you're going to be making this with your 3D printer. It's going to be 3D printed PLA. We want to give you some information on what the material properties are for PLA. And it's complicated a little bit, but the big idea is that it's strongest along the lines of the print, and it's weakest if you're trying to peel the layers or pull the layers apart in the direction that's orthogonal to the bed surface. And the approximate tensile strength for loading those print lines is about 60 megapascals. And the approximate flexural strength, that's if you printed like this and then bent, is about 80 megapascals. Now, if you try to pull it apart like this, the strength is about 20 megapascals. And if you really want to deep dive, there's a great paper that I spent some quality time with this afternoon. Now, PLA is not one of the default materials in SOLIDWORKS. but that doesn't really matter because you just need to know what the stress is, and you'll compare it to the allowable stress in your case. What you do need is something that has a reasonably similar elastic modulus, Poisson's ratio, and density. And well, not even density, you could just find out what the volume is and multiply that by the actual density of the material. But especially for FEA, having a similar elastic modulus and Poisson's ratio is nice. Acrylic is a good approximation for PLA. All right, so what are you going to do is you're going to look at this design, you start coming up with ideas for your component, sketch them, do some FBDs and stress analysis by hand. You're going to model some prototype ideas in CAD, perform FEA on them, and do that a few times to slowly hone in on a good design. And we'll be explaining these approaches in detail over the next couple weeks, and you'll be talking about it with your CA coaching session leader as well. And we're going to go through this process because it'll help us to develop a good design, and we'll have a good understanding of the space. We can explain why our design is good in our report, which is important, of course. The way that we'll evaluate it is that we will, you're going to test these components at home, and then you're going to upload data to an online spreadsheet. And let me pull that up. Okay, so you're going to pull up, you'll perform the test, you'll pull up this spreadsheet that's linked from the document, find your name, and then enter your data. What's the mass of your part? You'll weigh it on a kitchen scale and give the mass with an accuracy to the 10th or 100th of a gram. You'll enter your estimated factor of safety based on your own analysis. Then you'll enter the actual applied load that you measured with the bathroom scale, and you'll tell us whether your component held for 10 seconds or if it broke. If it held 1, broke 0. And then you'll submit a link to a video of you testing your component, link to a photo of weighing the component on that scale, a link to a photo of measuring component to make sure that it's 15 centimeters from rope connection point to rope connection point. That's one of the constraints here as well. And a photo of measuring the applied load. And if you are feeling up to it, an exciting bonus activity is keep adding weight until your component breaks. And that's the maximum load that it could withstand. You can use that to calculate what the actual factor of safety was. So you enter these things in on the spreadsheet, and then we'll calculate a few things, including your nominal grade and your performance grade, which I'll explain more in just a moment. Okay, so the way we're going to calculate these performance-based grades is we'll have this, 10% of your project grade will be simply, did you make a part? Did it meet the geometric requirement, like that length requirement? Could you tie the rope in and test it? And if you could do all those things, you qualify. You get 100% of your nominal performance grade. And that's 10% of the total project grade. And then the other thing is if your component does hold the load, how much did it weigh compared to the other components? And the lighter the mass of your part, the better, the higher this performance-based grade gets. And you can see the calculation here. Basically, you get, if you had the lowest mass component in the class, you'd get 12 points out of 10. And if you had the heaviest in the class, you'd get 0 points out of 10. And whoever designs the component that is the lowest, that holds the load, is going to get an award. Same thing for the best ratio of actual measured factor of safety to component mass, and also for the written report. So what's in that report? Well, you're going to submit a single PDF that's 3 pages long that has a summary page and 2 analysis pages. So the summary page will have a beautiful picture of your final design. It will have a couple hundred words describing what the design is, and really importantly, why you made these choices for your design. That's the real kicker here. Why is this a good design? And we are looking for very good writing, convincing explanations that leverage mechanical systems design ideas. So the kinds of things that we're talking about in class, those should show up in this summary. And you will probably need to edit it a bit. Just sit down and dash it off. It's probably not going to do the job for you. On that summary page, you'll also include some estimates of what the component mass should be based on your computer model, the factor of safety of the component, the load at which you expect it to fail, and how you expect it to fail when overloaded. Like, oh, this part will fracture or something like that. The next page will include your simple models and analysis. So this is like the free body diagrams, stress analysis, inverse analysis, and back of the envelope analysis kind of stuff. So hand analysis that guided the choice of the overall qualitative shape of your design and the values of the key parameters, like how thick this thing is, how long that thing is, the angle of this other thing. Those should be justified with back of the envelope analysis. And we'll talk more about how we're going to do that in the next couple weeks. And then your last page will be a summary of your CAD analysis, mostly finite element analysis, showing how you set up the FEA problem, what the stress, the predicted stress distribution in your part would be, and how it deforms under loading. And that first summary page is half of your report grade, and each of the analysis pages are worth a quarter of your report grade. So the total grade is that performance plus the report grade. All right, if you have any questions about this, feel free to shoot the team an email, or better yet, post it on Piazza, and you'll get a chance to discuss it all with in your coaching session.